Planetary surfaces create a deceptive feeling of clarity. We see the gray craters of planet Mercury, yellow clouds around planet Venus, blue oceans on planet Earth, red dust across planet Mars, and striped atmospheres on the giant planets. Most of the mass of each world remains hidden beneath that thin outer image. It exists under pressures unavailable in an ordinary laboratory, and at temperatures capable of melting most familiar materials. A journey toward planetary centers changes the meaning of common words. Rock begins to flow. Gas becomes liquid. Hydrogen acquires metallic properties and conducts electricity. Water mixes with ammonia and methane to create a hot, dense medium. Iron remains solid at temperatures comparable with the visible surface of star Sun, because immense pressure prevents the crystal structure from breaking apart. No machine has drilled more than a few miles into a planet. Most knowledge about planetary interiors comes indirectly. Scientists measure mass and size, track moons, study gravitational and magnetic fields, detect seismic waves, and observe rotation. Every measurement limits the range of possible interior models. Density provides the first clue. A world made of light gases has one interior profile. A rocky planet with an enormous iron core has another. Gravity reveals how mass is distributed. Tiny changes in spacecraft velocity show where heavy material is concentrated. A magnetic field points toward moving, electrically conducting fluid. Seismic waves change speed and direction when they cross boundaries between layers. Planetary shape adds another measurement. A rapidly rotating world bulges around the equator and flattens near the poles. The amount of flattening depends on rotation and the distribution of mass. A compact core produces one result. A diffuse central region produces another. Moons raise tides, and the response reveals how easily deep layers deform. Thermal radiation provides a view of hidden energy flow. A planet receives light from star Sun and returns energy to space. When the outgoing heat exceeds the absorbed sunlight, an internal source must exist. That source can include energy from formation, slow contraction, core crystallization, radioactive decay, or materials separating by density. The difference between received and emitted energy becomes a window into the depths. Laboratories create microscopic samples of planetary interiors. Diamond anvils squeeze matter between extremely hard tips. Powerful lasers heat it for fractions of a second. Shock facilities produce pressures found inside giant planets. Researchers measure density, electrical conductivity, and sound speed. Those results enter computer models. Every model contains uncertainty. Several combinations of composition and temperature can produce the same mass and radius. One type of measurement rarely solves the problem. Gravity must be combined with magnetic fields, heat flow, atmospheric chemistry, and rotation. Seismology is especially valuable for rocky worlds. On giant planets, atmospheric oscillations, gravity, and rings can play related roles. We will travel through all 8 planets, beginning close to star Sun and ending near the cold frontier of the solar system. The journey moves from the outside downward. Surfaces disappear first, followed by atmospheres and familiar states of matter. At the center of each world waits a different answer to one question. How did the same disk of gas and dust create 8 radically different interior machines? Planet Mercury. A world made almost entirely of core. Planet Mercury appears to be a small rocky world covered with ancient craters. Its radius is about 1,516 miles. Beneath the gray surface lies a metallic core with a radius near 1,289 miles. It occupies about 85% of the planetary radius. The rocky shell above it is only around 250 miles thick. That proportion makes planet Mercury exceptional among the rocky planets. The core of planet Earth is also large, yet a much thicker mantle surrounds it. Metal represents an unusually great fraction of the mass of planet Mercury. One possible history involves an early collision. A massive impact may have removed much of the young planet's rocky exterior. Other models explain the composition through conditions near young star Sun, where heat and chemistry in the protoplanetary disk affected the available building material. The surface preserves evidence of cooling. Long cliffs and scarps cross the planet. They formed as the interior gradually lost heat, the metallic core contracted, and the outer shell became too large. The planetary radius decreased, and the crust wrinkled like the skin of drying fruit. Part of the core remains liquid. A weak global magnetic field proves that a dynamo still operates. Generating a field requires electrically conducting fluid in motion. The outer region of the iron core probably contains melt enriched with sulfur and other light elements. They reduce the freezing temperature and help liquids survive for billions of years. The magnetic field is offset from the center. Northern and southern regions receive different protection from the solar wind. This may reflect unusual convection within a thin liquid layer. Planet Mercury shows that a small world can preserve an internal engine when chemistry slows the complete freezing of its core. During an imaginary descent, the first rocks would be broken by countless impacts. Greater pressure closes the cracks below. The rocky mantle remains solid while deforming slowly. The boundary of the enormous metallic core appears after only a few hundred miles. Its outer portion contains hot liquid iron alloy. Closer to the center, pressure may support a solid inner region. The dimensions of those layers remain under investigation. The great mystery involves lost history. The oversized core can be a result of birth conditions, collision, or several processes working together. New measurements of gravity, rotation, and surface chemistry must reveal how much rocky material the planet lost and how much it never acquired. Planet Venus. A twin of planet Earth with sealed depths. Planet Venus nearly matches planet Earth in size and average density. The basic model therefore appears familiar. An iron core occupies the center. A hot, rocky mantle surrounds it. A thin crust forms the top. The differences beyond that outline sent two similar worlds toward opposite climates and geological behavior. The surface of planet Earth is divided into mobile plates. They form at ocean ridges, collide, and sink into the mantle. This cycle transports water, carbon, and heat. Planet Venus currently appears to possess one connected outer shell. A global network of moving plates has not been detected. Heat reaches the surface through other paths. Radar maps show thousands of volcanic structures, lava plains, and large circular features known as coronae. Some coronae lie above thin, flexible lithosphere. Hot mantle material may rise in broad plumes and deform the crust. Several observations indicate recent volcanic activity. The outer shell can retain internal heat for long periods and experience major episodes of resurfacing. The lower portion of thickened crust may heat, become denser, separate, and sink into the mantle. This process returns material to the deep interior without a system resembling the plates of planet Earth. The state of the core remains unknown. Planet Venus produces no significant internally generated magnetic field. Several explanations remain possible. The core may be largely solid. Liquid metal may lack active convection. The slow rotation also changes the organization of internal flow. The missing magnetic field does not select a single answer. Planet Venus rotates very slowly and in the opposite direction from most planets. One spin lasts longer than its year. Slow rotation affects a dynamo, although it does not automatically prevent one. A magnetic field requires suitable heat flow from the core through the mantle. If the mantle removes heat too slowly, the liquid metal inside the core may circulate weakly. Imagine descending beneath the volcanic plains. A basaltic crust gives way to a hot silicate mantle. Under enormous pressure, rock remains solid and flows across geological time. Hot plumes rise in certain regions. They feed volcanoes and stretch the crust. Near half the planetary radius begins a metallic core whose state awaits future measurements. Planet Venus is a natural experiment. Two worlds received similar size and initial material. Planet Earth preserved oceans, moving crust, and a strong magnetic field. Planet Venus developed a super-dense carbon dioxide atmosphere and hides its internal dynamics beneath a continuous shell. Solving the core of planet Venus will help identify the conditions supporting a geologically active and habitable world. Planet Earth, a solid center inside a liquid metallic ocean. Planet Earth is the only world whose interior is monitored by thousands of seismic stations. An earthquake sends waves through the entire globe. Some waves travel through solids and liquids, others travel only through solids. Their disappearance, reflection, and refraction produced a map of layers thousands of miles below the surface. Continental crust averages about 19 miles thick. Beneath the oceans, it can be only a few miles thick. Below lies the mantle, extending about 1,800 miles. It contains most of the planetary volume. Mantle rock is almost entirely solid. Across long periods, it flows as hotter material rises and cooler material sinks. Mantle motion drives plate tectonics. Cold oceanic plates descend while hot material rises beneath ridges and volcanic regions. The slow cycle transports heat from the core and radioactive elements toward the surface. It builds mountains, opens oceans, triggers earthquakes, and participates in the long carbon cycle. At a depth close to 1,800 miles, the outer core begins. This liquid iron and nickel layer is about 1,400 miles thick. Temperature rises to several thousand degrees Fahrenheit. Rotation organizes the moving metal. The flow creates electric currents, and those currents generate the global magnetic field. The geodynamo helps protect the atmosphere from direct solar wind and guides charged particles toward polar regions, producing auroras. The field changes, magnetic poles wander, and the polarity has reversed many times across geological history. Frozen volcanic rocks and ocean crust preserve a record of those changes. At the center lies a solid inner core with a radius near 760 miles. Its temperature reaches roughly 9,800 degrees Fahrenheit, comparable with the visible surface of star-sun. Iron stays solid because the pressure reaches millions of times the pressure at the surface. The inner core grows slowly. Liquid iron crystallizes along its exterior, releasing heat and light elements. Those processes support convection in the outer core and help sustain the magnetic field. The inner core has complex texture. Seismic waves move through it at different speeds in different directions. Iron crystals may align during flow and growth. Some studies indicate an even deeper region with a distinct organization. The center of the best-studied planet still contains unknown details. The interior connects with surface life through a long chain. The core generates a magnetic field. The mantle moves plates. Volcanoes return gases to the atmosphere. Descending rock transports carbon into the deep planet. Continents and ocean basins are continuously rebuilt. The habitable surface is the upper skin of an operating planetary machine. Planet Mars, a cooling world with a liquid core. Planet Mars is smaller than planet Earth and lost internal heat more quickly. Its surface preserves ancient craters, giant volcanoes, and evidence of an era when rivers crossed the landscape. For decades, scientists estimated the interior from mass, rotation, and meteorites. The InSight lander placed a sensitive seismometer on the surface and began listening to Mars quakes. Seismic waves pass through the crust, mantle, and core by different paths. Reflections from internal boundaries constrained crustal thickness and core size. The crust proved heterogeneous and layered. Beneath the landing site, it may contain 2 or 3 major layers. Global average thickness depends on the model and the distribution of volcanic regions. The mantle consists of silicate rock and retains enough heat for occasional internal activity. Planet Mars has no modern system of plate tectonics. Its outer shell acts as one lid. Hot regions could remain in one place for immense periods. Volcanoes therefore grew for billions of years and reached extraordinary dimensions. The core contains iron, together with sulfur, oxygen, hydrogen, and other light elements. These ingredients lower density and the melting temperature. Seismic evidence shows a liquid region. New interpretations allow a solid inner core surrounded by liquid metal and a molten silicate layer above the core boundary. The model continues to evolve as old recordings are analyzed. Planet Mars lacks a strong global magnetic field today. Magnetized areas of ancient crust show that a dynamo operated early in its history. The internal thermal system later changed, circulation of liquid metal weakened, and the global field disappeared. Solar wind gained direct access to the upper atmosphere and contributed to its gradual loss. Planet Mars demonstrates the connection between size and time. A small world has more surface area relative to volume and loses heat more rapidly. Cooling reduces volcanism, changes the core, and weakens magnetic protection. Those changes affect atmosphere and the stability of surface water. Mars quakes are weaker than most destructive earthquakes. Scientific value comes from recording them cleanly. The InSight seismometer sat beneath a protective shield that reduced wind and temperature noise. Some events originated in active faults. Others came from meteoroid impacts. Waves from different sources illuminated the interior from different directions. A major event from the far side sent waves through especially deep regions. Analysis changed estimates of the core. Early models allowed an extremely large, low-density core. Later work introduced a molten silicate layer above the metal and produced a more compact central region. One new wave can reorganize an entire interior map. During an imaginary descent, red dust gives way to basaltic crust and a mantle preserving ancient chemical differences. A molten silicate layer may appear farther down. Beneath it lies a metallic core rich in light elements. At the very center, pressure may support a solid iron region. InSight transformed this outline from broad speculation into a measurable model. Planet Jupiter. A world without a surface and with an ocean of metallic hydrogen. Planet Jupiter consists mainly of hydrogen and helium. It has no solid surface for a spacecraft to reach. Upper clouds gradually merge into denser gas. Pressure rises, molecules move closer, and hydrogen becomes liquid. The boundary between atmosphere and interior ocean is diffuse. During a descent, sunlight would quickly disappear. Ammonia clouds give way to layers containing ammonium hydrosulfide and water. Temperature and pressure continue rising. Hydrogen becomes a dense molecular liquid. Deeper still, electrons separate from atoms, and the fluid gains metallic electrical conductivity. The liquid metallic hydrogen layer occupies an enormous fraction of the planet. Rapid rotation organizes the conducting flow. The result is the most powerful planetary magnetic field in the solar system. The magnetosphere extends millions of miles and holds dangerous radiation belts. The Juno spacecraft measured gravity and magnetism with high precision. Results changed the old image of a small, compact core. Heavy elements are distributed across a large central region and gradually mix with surrounding metallic hydrogen. Scientists describe the core as dilute or fuzzy. The diffuse structure preserves clues about formation. A large core of rock and ice may have formed first and rapidly attracted gas. High pressure later dissolved part of that core. A massive early collision may also have mixed the central region. The present distribution of heavy elements tests those scenarios. Helium rain may fall inside planet Jupiter. At certain pressures, helium mixes less effectively with metallic hydrogen. Droplets form and descend. Their fall releases gravitational energy. The process influences heat emission and the composition of different layers. Metallic hydrogen does not resemble molten iron. Hydrogen nuclei form a dense fluid, while electrons move freely. Laboratories can create this state only in tiny volumes for brief intervals. Inside planet Jupiter, it occupies a shell tens of thousands of miles thick. The magnetic field contains complex regional features. Juno followed polar orbits close above the clouds and found strong variation from place to place. Those observations reveal the depth of the dynamo and flow within the metallic hydrogen. Atmospheric jet streams may penetrate thousands of miles before electrical conductivity and magnetic interaction slow them. Pressure in the central region reaches tens of millions of surface atmospheres. Temperatures reach tens of thousands of degrees Fahrenheit. Rock and ice exist in states far removed from their surface forms. A distinct solid core boundary may never appear. Dense, heavy material can merge gradually into metallic hydrogen. Planet Jupiter emits more heat than it receives from star Sun. Some energy remains from formation. The planet contracts slowly and converts gravitational energy into heat. Interior flow reaches the atmosphere and helps sustain bands, vortices, and giant storms. Planet Saturn. A world with rain made of helium. Planet Saturn resembles planet Jupiter in basic composition. Its average density is much lower, and its mass is smaller. The hydrogen and helium atmosphere gradually becomes denser. Liquid molecular hydrogen appears below, followed by metallic hydrogen, and a central region rich in heavy elements. During its final orbits, the Cassini spacecraft measured gravity while passing between the planet and rings. The central region proved large and diffuse. Rock, ice, and metal may be distributed through a major fraction of the radius while mixing with hydrogen. The most famous internal process involves the separation of helium from hydrogen. Within a certain pressure and temperature range, helium forms droplets. They fall through hydrogen into deeper layers. Gravitational energy becomes heat. Helium rain helps explain why planet Saturn releases more energy than simple cooling models predict. Falling droplets influence composition. Upper layers gradually lose helium while deeper regions become enriched. Motion in metallic hydrogen creates the magnetic field. The field is remarkably symmetrical around the rotation axis. That geometry challenges ordinary dynamo models and points toward unusual layering in the conducting region. The rings provide another path into the interior. Oscillations in the depths alter gravity and excite waves among ring particles. The rings function as a giant seismograph. Their wave patterns reveal internal oscillation modes and the distribution of matter. Some ring waves require several closely spaced interior frequencies. This points toward a stably stratified region where composition changes with depth and limits free mixing. The dilute core may occupy a much larger fraction of the radius than older models of a compact rocky center suggested. Planet Saturn also contracts slowly. Gravitational energy becomes heat. Together with helium rain, contraction maintains internal emission. The planet continues evolving as materials separate and deep composition changes billions of years after formation. Deep pressure compresses hydrogen into its metallic state. Central temperatures reach many thousands of degrees Fahrenheit. Heavy elements do not have to form a separate solid sphere. They can dissolve and create a gradual transition. Planet Saturn resembles a multi-layer fluid system whose composition changes continuously with depth. Planet Uranus, an ice giant with a tilted magnetic heart. The term ice giant suggests a frozen sphere. The interior of planet Uranus is hot and dense. Ice refers to materials that condensed as water, ammonia, and methane in the cold outer solar system. Under planetary pressure, they occupy liquid and super-dense phases. An atmosphere of hydrogen, helium, and methane surrounds the deeper region. Most of the mass lies below in a hot mixture of water, ammonia, methane, and dissolved heavy material. Models place a relatively small rocky core at the center. Boundaries between layers may be gradual. At high pressure, water develops strange properties. In one possible phase, Oxygen atoms form a crystal lattice while hydrogen nuclei move through it. This material is called superionic ice. It is hotter than molten rock while combining ordered structure with high electrical conductivity. Diamonds may form deep inside planet Uranus. Pressure breaks methane molecules, and carbon joins into crystals that sink. This diamond rain remains a subject of experiments and theoretical research. It may transport both energy and carbon between layers. The magnetic field is strongly tilted relative to the rotation axis and offset from the center by roughly 1/3 of the planetary radius. That geometry suggests a dynamo operating in a shell at intermediate depth. An electrically conducting mixture of water, ammonia, and other components may create the field closer to the exterior than the metal core of planet Earth. Planet Uranus releases surprisingly little interior heat. Planet Neptune has a similar size and composition, yet emits much more energy. The weak flow from planet Uranus may be related to the ancient giant impact that tilted the world. A collision can reorganize layers and create a stable boundary that prevents heat from rising. Chemical separation provides another possibility. Weakly mixed layers trap heat below. The calm blue exterior can therefore conceal a hot depth isolated from the atmosphere. A future orbiter must measure gravity, magnetism, and thermal radiation with far greater precision. Sideways rotation makes those observations especially valuable. The magnetotail twists into a long spiral. During each rotation, the field changes its orientation relative to the solar wind. An orbiter could observe that cycle repeatedly and separate external effects from the signal of the deep dynamo. The exact water content is also unknown. The ice giant label can sound like a measured composition. Modern models permit a major contribution from rocky material dissolved and mixed at depth. Noble gases in the atmosphere could reveal the formation region and the amount of material captured by the growing planet. Planet Neptune, a hot interior ocean beneath the fastest winds. Planet Neptune is slightly smaller in diameter than planet Uranus and more massive, making it the densest giant planet. Its atmosphere consists mainly of hydrogen and helium with methane. Beneath the clouds, it gradually merges into a hot, dense mixture of water, ammonia, and methane. This region contains most of the planetary mass. Pressure keeps water in fluid and exotic states at thousands of degrees Fahrenheit. No familiar ocean surface exists. Matter forms a continuous deep medium in which molecules break and reorganize. Superionic phases and carbon crystals may occur. Planet Neptune radiates substantially more energy than it receives from distant star, Sun. Interior heat rises toward the atmosphere and helps support extremely fast winds. Frozen methane clouds can move above 1,200 miles per hour, several times faster than the strongest hurricanes on planet Earth. The extra heat may come from slow contraction, residual formation energy, and separation of materials. Deep layers may mix more efficiently than those of planet Uranus. Convection transports energy outward. The difference between the two similar ice giants remains a major mystery. The magnetic field is tilted and offset, resembling that of planet Uranus. This supports a dynamo in a conducting shell at intermediate depth. A hot mixture of water, ammonia, and methane components carries electrical charge. A small rocky core lies below. Only the Voyager spacecraft has completed a close flyby. Most interior models rely on gravity, shape, magnetic field, and laboratory physics at extreme pressure. An orbital mission could measure minute spacecraft acceleration and reveal the mass distribution. An atmospheric probe could determine outer composition and connect it with formation history. Deep water inside planet Neptune is far removed from a familiar transparent liquid. Chemical bonds continually reorganize under pressure. Electrical conductivity rises. The mixture can dissolve rocky and carbon-rich components. Simple shells of water and rock may represent only a convenient approximation of a far more complex medium. Planet Neptune and planet Uranus may have formed closer to star-sun and migrated outward, while giant planet orbits reorganized. Their interiors preserve evidence of that migration. The proportions of rock, water, and gas reveal which building blocks existed in different parts of the young disk. The interiors of all 8 planets can now be compared as 8 ways to store and release energy. Planet Mercury surrounds an enormous metallic core with a thin, rocky shell. Planet Venus hides an interior resembling that of planet Earth beneath a connected lithosphere and dense atmosphere. Planet Earth sustains a liquid outer core, magnetic field, and plate tectonics. Planet Mars cooled more quickly, preserved a liquid core, and lost its global dynamo. Planet Jupiter transformed hydrogen into the largest conducting ocean in the solar system and diluted its heavy core. Planet Saturn added helium rain and rings sensitive to interior oscillation. Planet Uranus trapped much of its heat beneath weakly mixed layers. Planet Neptune continues releasing internal energy that helps power the fastest planetary winds. The division between planet types comes from the properties of matter. Rocky planets separated into crust, mantle, and metal. Gas giants turned light elements into liquids and electrical conductors. Ice giants produced hot mixtures from water, ammonia, and methane. Pressure became the main architect of their interiors. Studying the layers allows scientists to read the past. Core size records formation conditions. A diffuse boundary points toward dissolution or ancient collision. Heat flow measures the efficiency of mixing. Magnetic fields reveal electrically conducting fluids. Seismic waves locate boundaries. The same modern radius can conceal different histories. One planet can possess a small rocky core and thick gas envelope. Another world of equal size can consist mainly of water and rock. Atmosphere changes the observed radius, and temperature expands gas. Without stellar age and composition, the correct interior model for an exoplanet remains uncertain. The solar system provides 8 control examples. Their masses are known through the orbits of moons and spacecraft. Their radii are measured directly. Some worlds have magnetic maps, gravity harmonics, and seismic recordings. Each new quantity reduces the space of possible solutions. This knowledge extends far beyond our system. Telescopes discover many worlds with sizes between planet Earth and planet Neptune, although our solar system contains no planet in that range. Understanding them requires models tested against the nearby planets. Planet Uranus and planet Neptune become keys to some of the most common known exoplanet types. The deepest point of every world remains inaccessible to a direct camera. We see the center through its influence on everything else. It changes rotation, shape, heat, volcanoes, magnetism, atmosphere, and moons. A planetary surface is the final page of a history written by the interior. 8 planets formed from one disk around young star Sun. Each received a different mass, chemistry, sequence of collisions, and cooling rate. Billions of years later, those differences created the iron sphere beneath planet Mercury, the geodynamo of planet Earth, the metallic ocean of planet Jupiter, and possible diamond rain within the ice giants. Depth transforms familiar elements into unfamiliar worlds hidden inside the worlds we see.